Okay, here's what we're going to try with our lab. We're going to see if we can actually calculate and, well, not actually calculate, but measure the permeability of free space. And so that permeability of free space is that funny looking mu with a little zero on it. It's equal to 4 pi times 10 to the negative 7 Tesla meters per amp. And the way we're going to do it is using this Slinky Jr. And we've stretched it out. I've stretched it out 50 centimeters. And what we've done is we've created a solenoid. And the solenoid actually has a magnetic field inside. So I've got the magnetic field sensor set up, so it's going to measure the magnetic field inside of my coil. And one of the things is I've got it hooked up to a particular voltage here. So it's hooked up to our power supply over here. And when I put current through here, if you follow the wire, it actually is going to send current below this coil and then over the top. So it goes below and over, below and over. So it's going around in this particular direction. So normally the right-hand rule is designed to actually have your thumb point in the direction of the current and then your fingers point in the direction of the magnetic field. I find that that's difficult with a solenoid, a coil like this. So instead, there's another version of the right-hand rule that'll work. If you actually take your fingers and curl them in the direction of the current, your thumb will point in the direction of the magnetic field. So since it's going below this coil, if I imagine my fingers going below the coil and then curving around to the top, my thumb would point in this direction, which is the same direction I have set up my magnetic field sensor. So that should give us our magnetic field sense in the correct direction. And we have it hooked up. We should be able to figure this out. Now, the way you actually calculate the magnetic field of a solenoid is this equation right here. So B, the magnetic field, is equal to the permeability of free space times little n times I. So I we know is current, and we know B is the magnetic field, and mu here, that's the permeability of free space. What is this little n? We had capital N before, which is the number of loops. What is little n? Well, little n is actually the number of loops per meter. So since I've stretched out my slinky to 50 centimeters, which is 0.5 meters, what I did is I also counted how many of these little coils there are in those 50 centimeters. And I stretched it out just perfectly so that there are exactly 50 coils in my 50 centimeters. So in other words, my little n here is actually going to be 50 over 0.5. So that's going to give me a value that would allow us to find the permeability of free space. Then what I've done over here on the computer is I've set up 3 different graphs. So I'm going to adjust this so you can see all the graphs really quick. So my graphs are designed to allow you to actually find not only the current and the magnetic field, but then I did one more graph at the bottom where I've got the magnetic field actually graphed versus current. And so with that, I should be able to find a nice straight line, and we should be able to get everything to work. I've got it so that basically everything is at 0, and I'm going to go ahead and start collecting my data. So as it collects data, you should see the currents in the magnetic field be 0. I'm going to turn on my voltage. Boom! There's my current, there's my magnetic field. It goes up. You can see the magnetic field line on that diagonal kind of coming out. And then when I'm going to turn it off, boom, it's going to go back to 0. And so you can actually see that your current and your magnetic field are related. We don't actually have a magnetic field when we have 0 current going through that coil, but the minute I turn on some current, I actually get a magnetic field. And look at this bottom graph down here. Looks very linear to me, which is exactly what we expect. The magnetic field should be directly related to your current, and the slope of that should actually give me not only the coefficient or the permeability of free space, but also my n. So it should be the product of those two. So I'm going to come up here, see if I can match a linear line to it, and I get a slope of 0.1096 milliteslas per amp. And we're going to go ahead, and it's a correlation of 0.9903. That's really good. We're going to calculate this out and see how close we get to the permeability of free space.